In this screencast, we introduce the impulse-momentum relationships for a rigid body. So let's start with what we know from particle dynamics and look at the expression that we have for the impulse-momentum relationship for a single particle. And we have the initial momentum, which is the mass times the inertial velocity at time 1, and then the momentum at time 2. And that's related by this impulse, which we express as a vector with a hat on top. And this impulse from time 1 to time 2, we say is equal to the integral of that force, of all the forces on point P, integrated across time from time 1 to time 2. Now what's special about this impulse is that the time itself is very short. So time 1 to time 2 is a small time, and that the force, F sub P, is a high force. And so by applying an impulse to a particle, this acts instantaneously because the time is so short and changes the momentum. So this means that we can start from rest and then apply a velocity as an initial condition to a problem when we're solving our equations of motion. That gives us our boundary conditions. Or if it's already moving, if the particle is already moving, when we apply this impulse, we change the momentum of the particle. So we can either change the speed or change the direction, or we can change both the speed and the direction of the particle. And now that we're dealing with rigid body motion, we have two governing laws. Our first law is that all the forces on the rigid body are equal to the mass of the rigid body multiplied by the acceleration as observed in the inertial reference frame. That's Euler's first law. And then Euler's second law we've stated as the time derivative as observed in the inertial reference frame of the angular momentum about the center of mass as observed in the inertial reference frame is equal to the sum of the moments about the center of mass. Now recall that we didn't come up with the impulse-momentum relationship for a single particle out of thin air, but instead we took Newton's second law and integrated it. So let's take Euler's first law and integrate this entire expression across time from T1 to T2. So we get the integral of our forces on the body from T1 to T2 dt, and then we'll write our expression in terms of our linear momentum of the rigid body. So this will be the integral from T1 to T2, which is a short time period, multiplied times the mass of the rigid body, multiplied times the time derivative of the velocity of the center of mass as observed in the inertial reference frame, the time derivative as observed in the inertial reference frame, and then dt. So we see that our dt's cancel, and so then that leaves us with the expression in which we have the integral of the force applied to the rigid body, which is the impulse on the rigid body. So I'll write that F sub g, we'll put a hat on it for the impulse, and we're integrating from time 1 to time 2. So this is a familiar expression. And then when we take this integral here of mg of our velocity, so it's mg dv, this will give us the mass of the rigid body multiplied times the velocity of the center of mass as observed in the inertial reference frame at time 2 minus the mass of the rigid body multiplied times the velocity of the center of mass as observed in the inertial reference frame at time 1. And then our final expression, we just rearrange our terms so we get the mass, the velocity at time 2 is equal to the mass of the rigid body multiplied times the velocity at time 1, and then add to that the impulse from time 1 to time 2. And so you can see that this expression looks just like the expression that we had for a single particle. And the reason why is because Euler's second law looks just like Euler's first law looks just like Newton's second law. The only difference is that instead of a single particle mass that we have here, we're working with the center of mass. And what this tells us, just like with the single particle, is that whenever we have the momentum of the center of mass at a particular time, we can apply a force anywhere on the rigid body. Because recall, that's what we're saying when we have the vector F sub g. So it's anywhere on the rigid body, and that's going to change the momentum, the translational momentum, immediately between time 1 and time 2 to this second expression here. So if we have a rigid body that's in motion, we can apply a force, and then it'll change its translational trajectory. Let's go through the same process for Euler's second law. To obtain an impulse-momentum relationship here, we'll take the time derivative from t1 to t2 across the entire expression, and so that gives us the time derivative t1 to t2 of the time derivative of our angular momentum as observed in the inertial reference frame. This is dt, and then we'll be taking the time derivative of our moment about the center of mass from time 1 to time 2. And then once again we see that our dt's cancel, and so we get the angular momentum about the center of mass at time 2 minus the angular momentum about the center of mass as observed in the inertial reference frame at time 1 is equal to an impulsive moment. So this is m, the moment about g, but it's an impulsive moment, so we put a hat on it or bar over top, and this is acting from time 1 to time 2. And so now with this expression, where we have the change in the angular momentum is equal to the impulsive moment about the center of mass, we can now apply an impulsive moment to get that change from time 1 to time 2. And once again, our time from t1 to t2 is very short, so it's almost an instantaneous change where we see a change in this angular momentum. And because we're in planar motion, and our angular momentum we express by our angular velocity, so it's angular momentum about the center of mass is equal to the moment of inertia about the center of mass, and then we say omega b as observed in I. And that's if we fixed a body frame b to the rigid body and we're in planar motion, then it ends up being the angular velocity observed in the inertial reference frame. So we can even rewrite this impulse expression as the angular momentum of the rigid body observed in the inertial reference frame at time 2 is equal to the angular momentum of the rigid body as observed in the inertial reference frame at time 1, and then this would be plus 1 over the moment of inertia multiplied times the impulsive momentum, or impulsive moment about the center of mass. And so we see here that when we apply an impulsive moment about the center of mass, we're changing the angular velocity of the rigid body. And this will only be in one direction. We only have an E3 or a B3 direction, what we typically define as out of the plane, because we're in planar motion. So we're only changing the magnitude of the angular velocity. But notice that we're changing the magnitude of the angular velocity as observed in the inertial reference frame. And that's because we're taking the time derivative of the angular momentum in the inertial reference frame, which always has to have the observation in the inertial reference frame. So we need to always be clear that we're referencing this to the inertial reference frame and not a non-inertial reference frame using the summation of our angular velocities like we've done before. One important thing to note about applying an impulsive moment is that if we have a rigid body, let's just say it's a rectangle that looks like this with the center of mass in the middle, is that when we apply an impulsive moment, we do this with an impulsive force. So we're actually going to be applying a force from T1 to T2 at some point on the body. So this means that in rigid bodies, these equations, these impulse momentum equations for linear momentum and then for angular momentum come as a pair, because if you can see here that whenever we apply this force, even if it's not at the center of mass, it's going to change the momentum of the center of mass, and then it's also going to change the rotational momentum about the center of mass. So keep in mind that when we apply an impulsive moment, that we need to use both of these impulse momentum relationships, because we apply an impulsive moment using an impulsive force, which will naturally bring about a change in the linear or translational momentum.